In this video, I'm going to explain how to analyze an in-cylinder compression waveform. This is a pressure waveform that is taken by removing the spark plug from an engine and inserting a pressure transducer. And by doing this, we can measure the changes in pressure that occur in the engine during engine cranking and running, and we can analyze the different events that happen during the 4 strokes of engine operation. In this particular waveform, on channel A, we used the pico pressure transducer. And on channel B, we used an inductive pickup to pick up the ignition signal from the ignition coil on that same cylinder. And I'll show you in a minute how we can use this ignition signal as well when we're analyzing this waveform. And personally, this is the way that I'd recommend that you acquire this signal. I would set up your scope so that you can record over a longer period of time. In this case, it was set up to record for 3 minutes. That wasn't necessary. Probably 1 minute would have been plenty. And during that time that you record, I would encourage you to set up so that as you're recording that you capture the cranking of the engine, startup, idling, and then perform a snap throttle test and maybe a wide open throttle test. And that's what's been done here. You can see that these changes in pressure happened when the RPM of the engine was changed. So the first thing that we're going to do is choose a section of this to zoom in on. You'll see on the red channel this is our spark. And all I really am after is this spike. So I can move this out of the way for now. And I want to zoom in on one 4-stroke event. So it should look something like this. And the next thing I want to do is I want to bring out these rulers over here on the right-hand side, which will mark off my 720 degrees of engine rotation. So there is TDC of the compression stroke. And we go through the 4 strokes, and this is when TDC of compression occurs again, 720 degrees later. I'll try my best to line these up with the peak of that compression stroke. And now we can see that we've marked off the 4 strokes. This is the power stroke, this is the exhaust stroke, this is the intake stroke, and this is the compression stroke. Of course, we have no power during the power stroke because the spark plug is out, so really this is just the piston traveling down. So let's take a look at this. This is when the piston is at top dead center on the compression stroke, so this is the highest point of pressure that will occur. And this is when the engine was idling. And we can look at the compression here. During idling, we should have about, usually it's between about 50 and 80 psi, but it varies a lot depending on the RPM of the engine and on the position of the throttle. And then you'll notice that during this stroke, from this point to this point, the piston is traveling downward. As the piston travels downward, the distance between the piston and the cylinder head increases and the pressure drops until it reaches a certain point down here, and the piston is still traveling downward, but while it is going down, suddenly the pressure in the cylinder begins to rise. Now what occurred there is the exhaust valve opened. And so I can bring over this ruler here and mark that off. Right here at the lowest point represents the point where the exhaust valve opened, right when it began to rise. And the reason the pressure rises is because when the exhaust valve is open, the pressure in the cylinder equalizes with the pressure in the exhaust manifold, and the pressure in the exhaust manifold should be very near atmospheric pressure. So if I bring this ruler down and mark off 0 psi, which represents atmospheric pressure because this pressure transducer is zeroed at atmospheric pressure. You'll notice that it is very near atmospheric pressure, which is good. In fact, exhaust back pressure should never be more than about 1 psi. If it's higher than that, that represents a plugged exhaust or a plugged catalytic converter. So I could use this to check for a plugged exhaust in a vehicle, and I would do this by revving the engine to a higher RPM and then measuring this, making sure that the exhaust pressure stayed at or below 1 psi even at the higher RPM. If the exhaust back pressure builds at high RPM, that indicates that the exhaust is plugged. From this point to this point, from 180 degrees to 360 degrees, the piston is traveling upward. But because the exhaust valve is open, we don't have a significant increase in pressure. Now at 360 degrees, the piston reverses and begins traveling back down in the cylinder again. Now before that happens, the intake valve opens. The intake valve usually opens at the end of the exhaust stroke. And it's hard to tell, but we would typically say that it opened right where the pressure began to decrease. So right in this area somewhere, the intake valve opened. It is difficult to identify exactly where that happened. But we should see the pressure kind of trailing off towards the end of that. And then somewhere right in about here, the exhaust valve finally closed. Now you remember that the piston is traveling downward now. The intake valve is open, so the pressure drops to negative because now the pressure in the intake manifold, which is negative, which is vacuum, is equalizing with the pressure in the cylinder. So if we wanted to bring this ruler down here, we could see that we have roughly negative 8 psi in the cylinder at this point, which tells us what our manifold vacuum is. And to convert that, just as a rule of thumb, you can double your psi reading to get inches of mercury. So that's around 16 or 17 inches of mercury of vacuum, or lower than atmospheric pressure that we have in our intake manifold at this point. So again, we don't see any changes in pressure because the valve is open as the piston is going down. One thing you should notice, though, is that this slope should happen at about 20 degrees after this TDC. So at about 380 degrees, roughly, is when you should see that. Now it's going to vary, and you'll see in a minute it's going to vary even on the same engine if you have variable valve timing. So we can see that the exhaust valve opened here, the exhaust valve closed here. The exhaust valve timing should retard with increased RPM, which means that it should happen later. We should see this move to the right or happen at a higher number of degrees during the 4-stroke cycle. Okay, so now we come to this 540 degree mark. This is where the piston begins traveling up. The piston moves upward, but we notice there is no increase in pressure until about this point right here. That's because the intake valve is still open. So we can come over here and mark off the point where the pressure begins to rise. Now this might be a good time, maybe I should have done this earlier, but maybe we should filter this just a little bit. I can adjust my filtering right here. I like to see a little bit of fuzz in the waveform, indicating that I still have a good clear picture with lots of definition. But right about this point here is where the pressure began to rise. That indicates very clearly that that is the point when the exhaust valve closed. So just as a reminder on valve event timing, this is the point we can see when the exhaust valve opens, and that's very clear and defined. This is the point where the intake valve closes. That's very clear and defined. Where the exhaust valve closes and where the intake valve opens, it's a little bit harder to see in here. We don't know that exactly sometimes. Usually there is an overlap because this is the point where the intake valve opens, and somewhere in here is where the exhaust valve closes, and that area would be called the valve overlap. Okay, now that we've been through that, let's take a look at what we can learn from this waveform. First, obviously, is we can see what the compression is in this cylinder. And around 60 psi is very normal for an idling compression. If we were to look at an earlier point in this waveform, if we were to move over here to the far left, we can see that during cranking, the compression actually was higher. That's because during cranking, the piston is moving slower, the valves are opening and closing slower, and we have a higher volumetric efficiency in the engine. So we were looking at a cranking compression of about 150 psi. We'll see that as soon as the engine started, which it looks like it started on the very second compression event because we had a spark right here and engine RPM increased, but we can see that as soon as the engine started, the compression began to drop because the engine was increasing in RPM. And here's our idling compression somewhere down here in the neighborhood of about 60 psi. Another thing that we can look at this point is ignition timing. So I'm going to zoom in on one of these events and bring my rulers over here to mark this off again. So if that's 0 degrees, we start at TDC, and that's 720 degrees. We can see that the spark occurred before TDC, as it should. But we can come over here and see exactly when this happened. And this is a useful tool sometimes when you're not sure if your ignition timing is correct. You come over here and it looks like it's happening at this point at about 23 degrees before top dead center. And that can be helpful, and we can see how that changes throughout the RPM range as well and under different load conditions. I'm going to zoom in here again closer on this. So one of the next things that we can tell about our compression is the quality of the sealing in the cylinder. And there are a couple of ways that we can see this. One is in the rise and fall of this compression waveform right here. During the compression and decompression strokes, they should be symmetrical. If you have a leaking valve or if you have worn piston rings where the cylinder is not sealing well, you'll see that it rises at a certain rate, but the pressure drops at a much faster rate because it's leaking. And so you'll see it coming down something like this at a steeper slope. Another thing that you can see, But on the rise and fall of this compression, it should be about equal, which means the point that we started at should be very close to the point that we end at. If this trough here is significantly lower than this trough, or if these are uneven, that also indicates that we have a compression issue in that cylinder. If I want to see what my RPM is at this point, I would bring out my rulers and mark off from there to there, and that should give me approximately the RPM. So our idle is a little high here. That is what it is. It's about 1200 RPM. So I can mark off at idle, and see the exhaust valve closes at about 148.4 degrees. We've got to remember that number. And the intake valve closes at about 594 degrees. Just to compare this, let's zoom out a little bit. And we'll come over here to a point where the RPM is much higher. You can see that the engine was accelerating. You can tell that because the compression pulses are getting closer together. So we can see that we've accelerated. If we want to measure that and see what our RPM is approximately, you can come out here and mark this off. And again, halfway in between, we were at about 3600 RPM there. You can see the pressure at this point almost reached 300 psi. Okay, if we zoom in closer on one of these, you'll see that the changes in pressure aren't quite as pronounced as they were at idle, but that's okay. We can come over here and mark our events off again. And we can still see that low trough. Remember, at idle, it was at 148 degrees when that exhaust valve opened. And now we're at 226 degrees when the exhaust valve opened. You can see that that retarded by almost 70 degrees. The exhaust valve is opening and closing later. We can now also pull this over and check our intake valve closing, which happened in a completely different stroke. Earlier it was happening over here during the compression stroke. Now it's advanced. The intake camshaft is advanced until it's opening now at 486 degrees instead of 594 degrees. And that's how we can test our valve timing and check and compare against specifications or against other events. I can also check my ignition timing again. Now at this RPM, our ignition time is actually happening at about 43 degrees before top dead center. So we can also see how our ignition timing changes under different RPMs and under different loads. Now lastly, I want to show you what I think is one of the most powerful ways you can use this waveform. I'm going to show you another waveform. On this particular vehicle, there was one cylinder that was misfiring, and they had decided that it was an engine mechanical issue and wanted to see if we could find out what was the cause of that issue. So what they did was they put a pressure transducer in the misfiring cylinder and then cranked the engine. You'll see that it cranked about 5 times right here. And then they put a pressure transducer in another cylinder of the same engine that was firing and was working correctly and did the same thing, and this is what they captured. Now ideally, I would recommend that you don't do this during cranking if you can help it. If the engine will run, start the car and let it idle. So these waveforms are from 2 separate cylinders captured under almost identical conditions. And then what I did was I used the reference waveform tool right here to create a reference waveform using one of these, and then I opened up the other waveform and then overlaid the first reference waveform on top of it. So these are 2 separate waveforms that are overlaid on top of each other. Now I want to line these up. It looks like the RPM at this point during cranking on the blue channel is very similar to the RPM that happened on the red channel at about this point. So we're going to try to line these up. So I want to see what the distance is between here and here so I can adjust my delay. So I want to move this blue reference waveform to the right so that it lines up with this. And I can see my distance is 10.98 seconds. That's the difference between the two. So I come down here to this blue box in the corner and I'm going to put 10.98 seconds in that box. Now I'm going to zoom in and see how we did at lining those up. That's not bad. And it is difficult to get those at exactly the same RPM. I'm going to pull these rulers out and mark off my 720 degrees just like we did before. So one of the very best ways to diagnose a mechanical problem with an engine cylinder is to compare it to another cylinder from the same engine, especially if you're having problems with one of the cylinders and not with the other. So let's mark these off. When you overlay the waveforms from 2 cylinders from the same engine, you should get a waveform that looks exactly the same. There should be no difference, especially if they're happening at exactly the same RPM. You can see as you look at this that the cylinder on the red channel is cranking at a slightly lower RPM. So it's slightly off, but it's not by much. Now let's look for any differences. The first difference I noticed is the compression. The compression on the blue cylinder is 140 psi during cranking, and that's good. When I mark off the compression on the other cylinder, and again this is during cranking, I get only 77. And anytime you have compression pressure during cranking that's less than 100, the engine probably won't start if you have multiple cylinders that low, or you'll have a misfire at idle on that cylinder. That's not high enough compression to have a firing event in that cylinder. So there's our first indication that something's wrong in that cylinder. The second thing we want to look at is any other differences. And you'll notice that because we were cranking and not idling, we don't have any back pressure during the exhaust stroke, so we don't have this to look at. But we can still clearly see these troughs. Remember we said that ideally we should see, if we draw a straight line across this, we should see the same pressure on this side of the compression as we do on this side of the decompression. And both of these cylinders had a lower drop, which gives us an indication that we do have some compression leakage. Now both of these compression peaks appear to be symmetrical, so I don't see a problem there. But this one has a much lower drop, which indicates a leaking compression. And also, I want to look at the timing here. Let's see if we can get an indication of what could be causing this. There's the opening of the exhaust valve on the cylinder on the blue channel. It happened at 134.2 degrees. Now on the cylinder with the red channel, the exhaust valve didn't open until 148 degrees. So right there is an indication of our problem. We have an exhaust valve on this cylinder that's opening later. Now we're off just a little bit here and we're off here, but that still is not enough to affect this. They should be exactly on top of each other, so we can see that we clearly have a delayed exhaust valve opening. So maybe a worn camshaft lobe or something along those lines on that cylinder. Because there are so many variations from engine to engine, it's hard to compare one engine to another. But it's really obvious that we should be able to compare one cylinder to another cylinder on the same engine, and they should have identical waveforms. So that's one of the most powerful ways we can use this to diagnose a mechanical problem within an engine.